Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your channel Chandan Physics. In this video, we are going to discuss FRESNEL'S theory of optical rotation, calculation of optical rotation, and experimental verification of FRESNEL'S theory. Let's begin. FRESNEL'S theory of optical rotation. We know that when plane polarized light is passed through optically active substances, then the emergent light is just rotated to an angle, and that is known as the angle of rotation, and the substances which are used to produce such angle of rotations are called optically active substances, and those substances which are not obeying that phenomenon, these are called non-optically active substances. Example of optically active substances are your quartz crystals, and example of non-optically active substances as your calcite crystal. Again, the angle of rotations, either it is rotate in clockwise direction or in anti-clockwise direction. On that basis, these are categorized further two in number. One is left-handed optically active substances, another one is right-handed optically active substances. So, FRESNEL proposed the theory regarding how that angle of rotation occurred in case of optically active substances. Let us come to the assumptions proposed by FRESNEL. According to FRESNEL, a plane polarized light on entering the crystal, that is along the optic axis, is resolved into two circularly polarized light, that is one clockwise and another anti-clockwise with the same frequency. Look here, if this one be the optic axis, this is optic axis, and plane polarized light is incident on that of crystal through that of optic axis, then what happened? Inside that of crystal, it is resolved into two components, that the two components are circularly polarized. This is the optic axis, this is the incident light, incident plane polarized light. According to FRESNEL, when plane polarized light is incident on the optic axis of a optically active crystal, then what happened inside this? That the plane polarized light is now divided into two components, two circularly polarized component. One such component along clockwise direction, another such component along anti-clockwise direction, and these two components have with same frequency. Okay. Next assumption, in optically active substances like quartz, the two circularly polarized vibrations travel with unequal velocities. As the optically active substances are divided into two numbers, one is left-handed and another one is right-handed optically active substances. On that basis, within this, the two components which are called circularly polarized have different velocities in such optically active substances. What are the velocity relations in this crystal? In case of right handed, which are also called dextro-rotatory quartz crystal, in case of right handed or clockwise component travel faster than the left handed or anti-clockwise circular component. In case of right handed, the right handed component travels faster than the left handed components. Again, in case of left handed or levorotatory quartz crystal, the left handed component has greater velocity than the right handed component. In the right handed or dextro-rotatory crystal, the right handed component travels faster than that of left handed component. Again, in case of left handed or levorotatory quartz crystal, the left handed component travel faster as comparison to that of right handed component. Due to the change in the velocities, difference in velocities, there will be also a phase difference in between these two components. As a result, a phase difference is produced between the two circularly polarized components when they propagate through the optically active substance like quartz. Due to the change in velocities in between these circularly polarized components, so they execute a phase difference in between these circularly polarized components. Okay. So, incident light and inside that of crystal, it is divided into two such circularly polarized component. One is along clockwise direction, another along anti-clockwise direction. After that, the two circularly polarized light recombine to form plane polarized light on emergence from the optically active substance. Inside that of crystal, they divide into two such circularly polarized component. One is clockwise direction, another one is anti-clockwise direction. After that, the emergence, this is the emergence plane polarized light. Plane polarized light incident and plane polarized light emergent, means these two circularly polarized components now superimpose with each other, and finally we obtain plane polarized light. These are the assumptions proposed by Fresnel regarding optical rotation. Now, using that assumptions, we can easily calculate what will be the angle of rotations. Means when plane polarized light is incident on a optically active crystal, then the property of optically active crystal is that it rotates that plane polarized light into some angle, and that angle is called angle of rotations. And these are some assumptions proposed by Fresnel regarding that polarization due to optical rotation. According to him, when incident plane polarized light on that of optically active crystal along that of optic axis, then it is divided into two circularly polarized light, one component along clockwise direction, another component along anti-clockwise direction, and after that the emergent light is also plane polarized, means these two circularly polarized components of light are now superimposed to produce the plane polarized light. On that basis of optically active substance as right handed or left handed, there will be a variation in velocities. As a result, there will be also a phase difference in between these two circularly polarized components. Let us come to the calculation of angle of rotation. Calculation of angle of rotation. Let the plane polarized light be incident normally on a quartz crystal. Quartz crystal is an example of optically active crystal. Quartz crystal plate that chord with the faces of perpendicular to the optic axis. Therefore, it is represented by the equation of simple harmonic motion. Let me consider this is x direction, this is y direction, and that y direction with the optic axis of that of quartz crystal, and light is incident on that of optic axis. Then it is divided into two such components according to Fresnel's theorem, Fresnel's assumption. One is left handed, another one is right handed. This is left handed, that is right handed, and due to the difference in velocities of these two circularly polarized components, there will be a phase difference. This is the right handed, this is the incident. So, the phase difference in between these two, let delta, and the resultant of these two evaluated like this. So, that plane polarized light now expressed as the equation of simple harmonic motion. So, y is equal to a sin omega t, whereas a with the amplitude of that of incident light, omega is the angular frequency which is 2 pi by t, t is the time period of incident vibration. According to Fresnel's assumption, what was the Fresnel's assumption? Any linearly polarized light is resolved into two equal and opposite circularly polarized components when that light enters that of quartz crystal. So, the equations of such components along two mutually perpendicular directions for incident light we can easily given as the x1 component as its amplitude a by 2, the entire amplitude now divided into along x axis as a by 2, along y axis another a by 2. So, the sum of the amplitudes be a along that direction. So, the components are x1 is equal to a by 2 cos omega t x component, and y component a by 2 sin omega t. Next, the x2 component minus a by 2 cos omega t, and y2 component a by 2 sin omega t. That angle depend, this is for clockwise circular components, this is for anti-clockwise circular component. For clockwise circular component, x1 a by 2 cos omega t with the angle of, this is the omega angular frequency, t with the time period of incident vibration. So, the x1 component now given as a by 2 cos omega t, y2 component a by 2, this is y1 component a by 2 sin omega t for clockwise circular component. Next, for anti-clockwise, so the x2 that is minus a by 2 cos omega t, y2 a by 2 sin omega t. Okay. As why it will be plus, this is the angle as minus omega t. So, sin of minus omega t as minus sin omega t, and it is anti-clockwise. So, there will be minus, so minus minus plus. Here cos of minus omega t as cos omega t, do not confuse. Why? This is negative sign, that is positive signs. Since it is clockwise direction, the angle treated as omega t. For anti-clockwise direction, it is treated as minus omega t. Okay. These two equations for the incident light. Next, but these two circularly polarized components travel through the optical active substance with different velocities. As we before clarifies, in that of Fresnel's assumptions, different velocities, so they execute a phase difference. What be the nature of that optical substances, then the velocity is depend upon what type of optically active substances are. Due to the phase difference, the equations for emergent components, let me say the phase difference be delta in between these two circularly polarized components. So the equations now changed. For incident light, as we say, x1 component a by 2 cos omega t, y1 component a by 2 sin omega t, but there will be a change in that of delta phase difference for x2 component and y2 component. So x2 component is written as minus a by 2 cos omega t plus delta, y2 component a by 2 sin omega t plus delta. So delta be the phase difference between these two circularly polarized components. Next, these emergent components now follow the principle of superposition. According to that principle of superposition, the resultant of two emergent circular vibrations is given by, for x axis another was along y axis. In x axis it is the superimposed of x1 plus x2, x1 plus x2. So the value of x1 as a by 2 cos omega t minus, for the value of x2 as minus a by 2 cos omega t plus delta. We simplify it, a by 2 as common, inside that bracket cos omega t minus cos omega t plus delta, cos a minus cos b. In trigonometric we use a formula as minus 2 sin a plus b by 2 into sin a minus b by 2. So that formula is used. So a by 2 as common, cos omega t minus cos omega t plus delta as minus 2 sin omega t plus delta by 2 into sin omega t minus delta by 2. So here omega t cancelled out, sin minus delta by 2, sin of minus theta as minus sin theta. So that's minus, that minus as plus, and here 2 cancelled out. So a sin delta by 2, that expression as omega t plus omega t, 2 omega t plus delta. So 2 omega t divided by 2, that is omega t plus delta by 2. So x now evaluated. Next, along y axis these two y components are superimposed. So y is equal to y1 plus y2. So the value of y1 and the value of y2 now superimposing with each other. The value of y1 as a by 2 sin omega t and the value of y2 as a by 2 sin omega t plus delta. A by 2 as common, inside that of bracket sin omega t plus delta, sin a plus sin b formula, 2 sin a plus b by 2 into cos a minus b by 2. So that trigonometric formula is used here, a by 2, 2 sin omega t plus delta by 2 into cos omega t minus delta by 2. Under solving it, omega t cancelled out, cos of minus delta by 2, cos of minus theta, that is cos theta. So a here 2 cancelled out, a cos delta by 2 into here omega t plus omega t, 2 omega t divided by 2, that is omega t plus delta by 2. Now along x axis and along y axis the circular vibration components are solved, as the x and y components having the same phase, they combine to form simple harmonic motions along a straight line. It has a same phase of delta by 2. So these two components now combine with each other to form a simple harmonic motion SHM, that is along a straight line. So the resultant of these two as r is equal to x square plus y square under root. So the value of x and the value of y its whole square under root. Inside that of bracket we take common as a square sin square omega t plus delta by 2, and inside that bracket there will be a term sin square delta by 2 plus cos square delta by 2, that is 1, and taking the under root, finally we obtain r is equal to a sin omega t plus delta by 2. This is the equation, and that equation represent the equation of a straight line, that is the SSM. So it is proved that when an incident light, plane polarized incident light to that of optically active crystal, example as quartz crystal, and then it is divided into two such circularly polarized components, and finally we obtain also the plane polarized light. So the emergent light from the crystal is plane polarized. The emergent light from the crystal is plane polarized, but it is inclined to y-axis at an angle delta by 2. So that angle easily can be calculated as dividing x by y. That component cancel out, a cancel out, sin delta by 2 divided by cos delta by 2, that is tan delta by 2. X by y is equal to tan delta by 2. Next, our aim is to calculate what will be the angle of rotations. That angle of rotations we can calculate it by taking the relation. As you know, phase difference is equal to 2 pi by lambda into path difference. Here phase difference is delta, 2 pi by lambda. Now the path difference is calculated. As we say, mu L is the refractive index for left-handed circularly polarized light, and mu R is the refractive index for right-handed circularly polarized light, and D be the thickness of that of crystal plate, which crystal we taken into consideration, and that is a crystal of left-handed optically active crystal. For that of left-handed optically active crystal, the velocities of left-handed such component is greater than that of velocities of right-handed circularly polarized components. Here mu L is greater than mu R as we taken, therefore the path difference will be mu L minus mu R into D. This is the phase difference expression. So the angle of rotation of such plane polarization, that is theta is equal to delta by 2. Theta, the angle of rotation is equal to delta by 2. So the angle of rotation theta is equal to delta by 2. The expression of delta is that one. So delta by 2. Now 2 is divided. It will be pi d divided by lambda into mu L minus mu R. Mu L refractive index C divided by VL. C is the velocity of light divided by velocity of that ray in that particular medium. So VL is the velocity of left-handed circularly polarized light, VR is the velocity of right-handed circularly polarized light. C as common, pi d C divided by lambda into 1 by VL minus 1 by VR. So C is equal to lambda by T, where T represents the time period. In the expression for C, we substitute lambda by T. So lambda lambda cancel out, and finally the expression for angle of rotation is evaluated as angle of rotation theta is equal to pi d divided by T, in that of bracket 1 by VL minus 1 by VR. This is the required expression for angle of rotation. So by using that Fresnel'S theory, we evaluate the angle of rotation as plane polarized light incident normal in that of quartz crystal. So the expression is simple harmonic. Then by using Fresnel'S assumption, they divided into two such circularly polarized components. The components are given as for clockwise and for anti-clockwise. Next, due to the phase difference, so there will be a change of phase difference change, and simplifying it by taking the principle of superposition along x axis, the two components of x's are added. Next, for y axis, the two components of y are added, and finally these two have the same phase, therefore that resultant is nothing but a plane polarized light. And finally, using that phase difference concept, the angle of rotation for that plane polarization is mathematically calculated. Next, we can experimentally verify that FRESNEL'S theory. What exactly say the FRESNEL'S theory? When a plane polarized light is incident on a optically active crystal, then that optical inside that of optically active crystal, that the plane polarized light is divided into two such circularly polarized components, one along clockwise direction, another along anti-clockwise direction. After that, these two are combined, and finally at that of emergent we also get plane polarized light. So how? Experimentally, that is verified by Fresnel. Fresnel used a large number of alternate right-handed and left-handed quartz prism. Quartz is that material which is optically active material, and that prisms are made in that of quartz crystal, and these prisms are to form a rectangular box, and here it is arranged in such a way that the optic axis of each prism is parallel to its bases. So how we arrange? This is right-handed quartz prism, left-handed, right-handed, left-handed, right-handed, left-handed. In such a manner, these quartz prisms are arranged, so the optic axis of these prisms are parallel to its bases, and they form a rectangular box. So when plane polarized light, this is plane polarized light is incident on such arrangement. So due to the property of that quartz crystal, so it is divided it into two components, and due to such arrangement, one such components are deviating like this, and another such component deviating like this, and that deviation is the left-handed circularly polarized component, and this deviation is the right-handed circularly components. So how we can say that component is left-handed and this component is right-handed? Think that when circularly polarized light, circularly polarized light passes through a quarter wavelet, then at that of output we obtain plane polarized light, plane polarized light, and that plane polarized light can be analyzed by using an nickel prism as an analyzer. If under that full rotation we obtain two maxima and two minima, then we confirm that this one is circularly polarized light as we enter through that of quarter wavelet. So, here when plane polarized light is passed through the arrangements by Fresnel. So, it is split up into two such components as left handed and right handed. These two are either circularly polarized or not, can be verified by taking a quarter wavelet and analyzing it through the nickel prism as an analyzer. That the plane polarized light, nickel prism as an analyzer. Then it is experimentally verified as that Fresnel's assumption regarding optical polarization, optical rotation polarization. So, here we experimentally verified that Fresnel's theory regarding optical rotation polarization. So, with the help of this video lecture, we understand Fresnel's theory of optical rotation, assumptions proposed by Fresnel, and by using that Fresnel's assumption of optical rotation, we calculate the angle of rotation mathematically. The angle of rotation is calculated, and finally we verify that Fresnel's theory experimentally it can be verified. So, with this useful and informative notes, let me wind up the session. Thank you.